This is the circuit diagram of the BusyBox. Apologies if my hands look really dirty. I think it's something to do with the lighting. They're not really as dirty as they look. At the center of the circuit diagram is the Raspberry Pi Pico. I buy these in normally 3 at a time, and with postage they are $21 for 3 Australian dollars. I buy them just the bare board, and I solder these pin headers to them. These ones are extended pins so that I can plug it into the main circuit board, and then I can plug test gear or further circuits into the top for developing the circuit board. Eventually I would generally swap this out for the final circuit for one with normal pin headers to plug into the circuit. I always like to plug them in because you never know when you're going to brick them and have to pull them out and replace them, and you don't really want to be desoldering 40 pins. So that's the Raspberry Pi Pico. Fantastic little board with all its memory and so on the board, and the programmer socket here. It's actually that way around. Programming and power socket here for temporary power. The BusyBox works under battery power typically. There's a 3.7 volt single 18650 lithium cell here, and it is charged with this charge and discharge board. This takes care of the charging of the battery to make sure that the charging profile is correct. Lithium batteries need a certain charging profile, and also they need to be discharged, not over discharged, and this board takes care of that as well. So when they go from 4.1 volts down to like 3.6 or something, the board will shut them off, and you then recharge the circuit. It's got some little indicators for charging and charged and on and all the rest of it. There's this charging socket here, but I don't use that. I've in fact put these 2 sockets. They're a little socket on a board, and I put 2 in so that they're redundant if one fails. And they charge this circuit, and this circuit charges the battery, and then this circuit also gives power out. This is the on-off switch, and this is a poly fuse, which is a resettable fuse, 1100 milliamps, just in case anything goes badly wrong and the circuit tries to draw too much power. From this module, we go to this voltage step-up module, and this is because the circuit needs 5 volts in places, and the battery only gives between 3.7 and 4.1. So this has a variable pot here, and that's adjusted so the voltage out here is about 5.2 volts, because I wanted to get a reasonable amount of power for the 5 volt amplifier down here, which I'll cover in a minute. And I didn't want it drooping below 5 volts because I want the maximum amount of audio power. This goes into this FET, P channel FET, and this is a device that stops the USB power supply fighting with the battery power supply if they're both on at the same time, and it will block out the higher of the 2 voltages. So that's a kind of safety thing. Although if I had my time again, I'd probably take 3 or 4 volts direct from the battery into the Pi Pico, because it can take a range of voltages. So that deals with the power supply section. This is the Catalex audio MP3 card. This is kind of what it looks like. An SD drive, an SD card goes in here with all your MP3 files on, laid out in a certain type of folder structure, and then those MP3 files are called up via a UART communications, UART transmit and receive from the Pico. So this card, you can tell it to play a certain track from a certain folder, and it will reply saying whether that track is present, whether there's been an error in playback, when the playback's finished. You can also ask it, as we do, how many sound files are in the folder. So you can add sound files to the folder, and then the Pico on turn on will inquire how many sound files are in that folder, so that it can play one at random from any number that you've put in automatically. So there's a transmit and receive function from this card. You see this little wire here. This is not present on the busy box, but this is an extra wire that I've soldered for future projects, whereby this pin natively changes state when the audio file is finished. So you can just pull that pin rather than having to decode a UART text string or whatever. It's just probably a simpler way to just find out when a file is finished. It's important to know when a file's finished, because if you're announcing a score or something, you don't want gaps between the announcements. So that's quite an important feature of the card. The audio output of the card goes into this little amplifier, and this is a 5-volt amplifier. It's got a volume control on it, but in fact it's not shown on this circuit diagram, but I've replaced this pot with another pot on the underside of the box to give volume control. The little chip here, when it's working hard, needs a heat sink. It gets quite hot, and it has a 5-volt supply, and it powers these two speakers, which are just two speakers I had, which are of the correct size to fit into the busy box. They're reasonable quality, but their impedance was a bit low, so I put two of them in parallel. On this side you can see the piezo Siren, which is powered by a N-channel FET transistor, and this just turns it on and off, just to annoy the parent as much as possible. And this switch here is the lock switch. It's the micro switch which is attached to the lock, which is just an on-off input into the Pi Pico. These module boards here are Hall effect switches, such as that one, and this is the Hall effect sensor, which senses a magnetic field from a nearby magnet. These boards typically have an analog and a digital output. The analog output is adjusted by this, and the digital output is on or off. It's got LEDs to show power and on off. So there's 1, 2, 3, 4, 5, 6 of those, mainly associated with the jigsaw pieces, and also the cogs. So that's an on-off Hall effect switch. And these four are just the coloured switches. They're all of these are just input pins on the Raspberry Pi Pico. Here we got the circular LEDs. These are WS2812 variety in a circle, 8 of them. And they require a specific protocol to drive them, and that protocol requires quite a fast refresh rate from memory, hundreds of kilohertz. So that can't be done by just bit bashing on the Raspberry Pi. The Python's not fast enough to do that. And it's not a common protocol which is provided in hardware on the chip, such as SPI or I2C or UART. It's a strange one. So somebody has written a Python module which uses one of the state machines on the Raspberry Pi P2040 chip. The chip is got two general processing cores running at 130 megahertz, which is great. Only one of those is used on the busy box. It also has 8 state machines, and each of these can run a little bit of machine code, assembly code, at a rate of 130 megahertz. So and they have a buffer which reports back and forth to the main core. So the main core sends out this data into the buffer, and then the main core can get on with whatever it's doing, because the state machine has a little program with them which sends the correct protocol to the LEDs. These LEDs are 5 volts, and the data in, the high value is typically 0.7 times 5 volts, which is 3.5 volts. So the 3.3 volts of the Raspberry Pi is a little bit low to get a high signal on these. Sometimes it works and sometimes it doesn't. For reliability though, I've got a level shifter here, which looks like there's one, that's a 2-channel level shifter, but in fact this one is a 4-channel level shifter, and this is quite a clever little circuit in that it'll shift 3.3 volts up to 5 volts, or it'll shift 5 volts down to 3.3 volts. Here's the actual 4-channel one that I'm actually using here and here, although not all of the channels are used, and that takes the data from the Raspberry Pi and produces a 5 volt high data, and obviously 0 volts low data into the LED. This is similar. This is an 8x8 red LED display. This interface is a standard SPI interface, which is great. Makes it reasonably easy. I've written my own driver for that because I didn't like the drivers on the web. And again, this is a 5 volt display, so it has a level. It goes into the level shifter as well for its data and clock lines. This is a real-time clock calendar, which kind of looks like this. This is the board. On this particular one, I've taken off the backup battery, which is a coin cell on the back, and I've put in a supercapacitor, because on a lot of my projects I prefer a supercapacitor, which should have, you know, hopefully an indefinite life for battery backup, and in my experience they last for a couple of days without power, in terms of keeping the clock calendar running. This is a DS3231, I think it is. Oh, not the camera. 3231, a chip which has an accuracy of, I think, a few minutes a year, and it also comes on the board with a little EEPROM memory there, which is used in the busy box to store things like status of options and favorites list of music and so forth. Both of these are accessed through the same I2C or I2C interface, and they both have different addresses on that interface. Quite easy to access. So that's the clock calendar. And down here we have another level shifter, and we have the LED strip, the 24 LED strip, which is an APA 102 a multicolored LED, and this multicolored LED has a fairly simple protocol, and these are the clock and data from the level shifters for this AP 102, which tends to be a kind of text stroke hex sort of protocol. So that's it really, not a very complicated circuit, a lot of bits and pieces. When, as you can see, I prefer to buy all of these boards sort of ready-made to save having to muck around with lots of resistors and capacitors and support components. And I just search for Arduino real-time clock calendar, Arduino Hall effect switch, Arduino level shifter, and so on, because a lot of these were originally developed for the popular Arduino system, and it's just so cheap it's hardly worth bothering with buying individual components. Some of these cases the board is actually with everything on is cheaper than just buying the individual chip itself, which is just seems to be the way of the world these days. Okay, that's it.